Today we study Ampere's law. Ampere's law states that the magnetic field is due to a current can be calculated followed by Ampere's law. First of all, we consider the direction of the magnetic field. Suppose that we have a current I, and magnetic field is generated around that current on the plane counterclockwise when seen from the direction of the current. The head of the arrow, seen from the head of the arrow, it's rotating counterclockwise. What is magnetic field? On the cross-sectional plane, if the current is flowing out, then the magnetic field is counterclockwise. If the current is into the plane, then the magnetic field is clockwise. Current I is flowing along the z-axis, that is perpendicular to the xy plane, plus z-axis going out of the page, plus c. This is a plus c, then magnetic field is counterclockwise, and when it enters into the page, then magnetic field is clockwise. In addition, the strength of the magnetic field decays as the distance perpendicular. This rho is square root x squared plus y squared, where coordinate x comma y on this xy plane, and origin is there. This rho is square root of x squared plus y squared. The magnetic field at rho is tangent to the circle. Either this direction, depending on the direction of the current, or that direction. In any case, tangent to the circle. This symbol stands for the current that is coming parallel to decay, that is coming out of the page. And cross sign stands for the current going into the page. At point P, usually we use a P for the field point. Field point represents the point at which the electric field or magnetic field are measured. There are two unit vectors. There is a right triangle, angle phi. Then the radius is 1. Then it's cosine phi, sine phi. If there is a right triangle with radius 1, right triangle, then this is the angle theta, angle phi. It is 1, so sine phi cosine phi. So to denote this unit vector, we use the coordinate cosine phi, sine phi. If it is a unit circle, the coordinate of this point is minus sine phi cosine phi. We know that the radial vector, the planar radial vector on the plane xy plane has the coordinate this. So we have x coordinate cosine phi, y coordinate sine phi for the planar radial vector. This is tangential vector. Tangential vector has a coordinate minus a sine for the x component, minus a sine, cosine for the y component. So we have rho hat, that is planar radial vector, and tangential vector phi hat, that is minus sine phi, cosine phi. Radial cosine phi, sine phi. Okay. In the calculation of magnetic field, we frequently compute the cross product, so we review the cross products. Cross product A cross B equals AB absolute value sine phi, where phi is the angle between A and B. The direction of n hat is normal to the plane made of A and B, and the direction of n hat is either in this direction or that direction. But we do not choose this one. Instead, we choose a part of a cake, A, B, and n hat. So you use the right hand, your fingers, swipe your fingers, and then your thumb is parallel to the n direction. Okay. As a result, we have I cross j equals k, j cross k equals I, so I, j, k. I cross j equals k, k cross j equals I, j cross k equals I, j cross k equals I, and k cross I equals j. And we have anti-commutation relation. B cross A equals minus A cross B. A cross B equals minus B cross A. In a similar manner, I, J, K, they form a cyclic triad. Cyclic triad means they satisfy the cross product ij equals k, jk equals I, ki equals j. In a similar manner, rho, phi, k, they also satisfy the cyclic triad. So rho cross phi equals k, phi cross k equals rho, k cross rho equals phi. If you change the order, you flip the sign. Biot-Savart law. It is parallel to the Coulomb's law. In the E field. This is for the E field, this is for the B field. Once you understand this, then you next use Gauss' law. Computation of the electric field, making use of Gauss' law, is very simple, but it is useful only when there is a symmetry. In general, we have to use Coulomb's law. In the case of magnetic field, in general, Biot-Savart law tells us everything. But when you have some symmetry of the system or current, then you can make use of Ampere's law that we learn later. So, Biot-Savart law is a parallel to the Coulomb's law, and Ampere's law is a parallel to the Gauss law, and both Ampere's law and Biot-Savart law is for the magnetic field. Gauss law and Coulomb's law are for the electric field calculation. Coulomb's law was F equals 1 over 4 pi epsilon 0 Q1 Q2 R squared. R is the distance between the two charges, and R hat is a unit vector connecting the two charges, and direction is either plus or minus depending on the one and two, the direction for the force applied to particle 2, 1 to 2, then this is the direction. This is the direction for the force on particle 1 from 2. And then the product of the charges changes the sign. So if the product is positive, the force is repulsive. The product is negative, then the force is attractive. So then in that case, it flips the sign, direction of the force. In a similar manner, if there is a straight current, the magnetic field surrounds. This is magnetic field, and this is current I. But Biot-Savart law is for the case of general current, that doesn't have to be the straight. Instead, the current can be flowing arbitrarily. Just like this. So current I tangent is this. Current I is flowing in this direction. So we choose the small current segment, and we have a field point P. Field point. Then there is a radius vector, R vector, that connects the current element from the current element to the field point. And we have a unit radial vector R hat. In the Coulomb's law, overall vector was 1/4 pi epsilon, that is electrostatic constant. In the magnetic field, we have 1/4 pi, the same, but we have a factor mu 0 in the numerator. And this mu 0 is called permeability constant. Permeability constant. It depends on the material, but we restrict ourselves to the vacuum. The dimension of the permeability constant is, the SI unit is this. This is Tesla for the magnetic field, meter per ampere. We have length squared, and this magnetic field that has the unit Tesla. Next, the current is proportional to current, linearly proportional to the current. And the direction and in addition, ds, this is a vector, the linearly proportional to the length. And the direction is determined by the cross-section, this cross product. R hat is the unit vector connecting parallel to the direction, connecting to the current element, this current element, and the field point. ds is here, ds cross r, the cross product, because if we draw these two vectors, ds vector and radial vector on a plane, the direction of ds cross r is into the page. That's the reason why this sign is, the symbol is written on point P if the current I is positive. So according to this 1/r squared, Usability law is also an inverse square law. If there is an angle theta between ds, the current element, and the radial vector from the current element to the field point is the theta. The magnitude depends on the sine theta. Let us compute the electric field due to a current in a long straight wire by making use of Usability Law. We compute the magnetic field around the straight wire. This is a straight wire along the z-axis. So this is a z-axis. The current is going up along the z-axis. Then the magnetic field is rotating counterclockwise when it is seen on top. It is convenient to use cylindrical coordinates. So z-axis is here, and cylindrical coordinates. Origin, x, y, and z. And we choose, for simplicity, this is a long straight wire on the infinite plane. It's better to choose the xy plane, that is, the field point is on the xy plane. And this is rho. Rho is the perpendicular distance from the current. I is the following. The rho is the perpendicular distance. Before we obtain the result, we already expect that magnetic field is rotating counterclockwise because of the symmetry. The symmetry states that this amount, the upper half, and this amount, the lower half, they contribute the same amount. So there is no way to have the magnetic field either plus z or minus z direction. Usability law states that the differential magnetic field due to the differential current element is this. We have to memorize this. Over a factor, permeability constant divided by 4 pi multiplied by the current I and current segment cross unit vector that connects the unit vector that connects unit. This is ds and unit vector that connects. This is r, and unit vector is r hat, and this field point p, and we choose the field point p whose coordinate or z coordinate is 0. The length element of the current carrying wire at z equals this one, dz k hat. So this direction is k hat, dz k hat. Okay. The displacement r from the current segment. The current segment is placed here. Current segment is placed at 0, 0, z. And field point is xy0. xy0 subtracted by 0, 0, z. Therefore, the radius vector that connects the current element to the field point is this. What is the unit vector? Unit vector is this vector divided by its length. Well, this is x squared, y squared, plus or minus z squared. Minus g squared is g squared. The perpendicular distance rho from the wire to the field point is perpendicular distance rho. Perpendicular distance rho. This is the displacement, and the distance is magnitude of this. So therefore, this one is rho squared. So this is rho squared plus z squared. The vector ds cross r hat. We need to compute the ds cross r hat. ds cross r hat. ds is here. Substitute. Easy. K hat. R hat. 1 over r. X I y j minus a z k. Now k cross k disappears. K cross I equals j. So k cross I equals j. This is x. Y. K cross j equals minus I. So y have an additional negative sign. Because this magnitude is rho, if we factor out rho, what we have is this one is dz rho over r minus y minus the sine theta, the sine phi I, cosine phi j. This is a unit vector along the tangential direction. So this is, as a result, is proportional to phi hat. The differential magnetic field due to the differential current element can be expressed as, now we substitute this result into here. Then mu 0 I 4 pi r squared multiply r cubed in the denominator. Rho is here, and dz is here, and unit vector phi hat is here. Now r is this. So substitute r in here. Then rho squared g squared, 3 halves. And we rescale the variable. Z is rho alpha. And this is length, this is the length. So this one alpha is dimensionless. It's dimensionless and runs this coordinate z runs from minus infinity to infinity. So alpha runs from minus infinity to plus infinity. We have an integral. We have to evaluate this integral. But if you compute the derivative of this, we'll find this. Therefore, we can make use of this one to find out the integral from minus infinity to infinity. The result is equals alpha 1 plus alpha squared, alpha goes to infinity, subtracted by alpha over 1 plus alpha squared, alpha goes to minus infinity. You know, alpha over 1 plus alpha squared goes to alpha squared alpha is alpha over alpha absolute value as alpha goes to plus minus infinity. So it is plus 1 or minus 1. Plus 1 as alpha goes to infinity, alpha goes to minus infinity, it becomes minus 1. Therefore, this value is 1 minus minus 1 equals 2. We have 2. Now, we have overall factor and constant unit vector. Overall factor, constant unit vector, as this integral equals to 2. And if we multiply 2, we end up with the final result for the magnetic field that is generated by a straight current along an infinite wire. Then the magnetic field is surrounding the current, and its magnitude is this. Next, we consider magnetic field due to a circular current. The previous case, it was a straight current, and this is a circular current. A circular current I of radius r, centered at the origin, is flowing on the xy plane. This is xy plane. We compute the magnetic field at the field point 0, 0, z. 0, 0, z. Field point is on the normal, along the z-axis. On the symmetry axis, this is the symmetry axis. We use the cylindrical coordinates rho, this rho, square root x squared plus y squared, where x and y are coordinates of the wire element, phi azimuthal angle for the wire segment. The unit vectors for the cylindrical coordinates to represent the differential wire segments are, we have rho direction and phi direction. So rho direction, I hat, j hat, cosine psi. Phi direction, tangential direction, is a minus sine phi, cosine phi. Right, ds is at this point, the angle phi, and p is 0, 0, z. P, field point is here, and ds is here. Differential length element is rho d phi, phi hat. Rho d phi, phi hat. phi hash is here. R vector. This is R vector that connects the Y element to the field point. So field point coordinate, that is a zk hat, subtracted by this rho hat. We know k hat and rho hat are perpendicular to each other. Therefore, the magnitude of this vector, magnitude is square root z square plus rho square in here. So unit vector along the r direction, unit vector along the r direction is this. Next, we compute the ds cos r hat. This one is necessary to substitute to the Usability Law. ds is here. ds is here. We substitute ds, and r hat is here. ds r hat. We remember rho, phi, k hat, they construct a cyclic triad. So rho phi equals k hat. So phi equals rho is minus k hat. Phi equals k hat is minus phi equals rho, phi equals rho. So minus k hat. So this minus rho becomes plus rho. The phi k. Phi cos k, according to this, phi cos k equals rho. Phi cos k equals rho. So z rho hat. So this is this. And substitute this result in here. We have mu 0 I, denominator is 4 pi, r, what is r? R is here, and this one is r. So r squared, and we have additional r, so r cubed is z squared plus rho squared, 3 halves. And numerator rho d phi, and 0 hat, rho k hat. Alright. Now we integrate over phi. Z, rho, they are independent of phi. Only phi dependent one is rho hat or phi hat, but we do not have phi hat, we have rho hat only. This is rho hat, and rho hat I hat cosine phi plus j hat sine phi. So if we integrate this one over phi, this one equals 0. 0. So rho hat component vanishes, and only k hat component survive. And k hat is independent of phi, so integral d phi is just 2 pi. As a result, we have rho squared in the numerator, rho squared, there used to be 4 pi in the denominator, but integral defined 2 pi, so that cancels to have a factor of 2 in the denominator. This one we can rewrite rho cubed 1 plus z squared over rho squared 3/2. And this rho squared, a rho cube, and numerator has a rho squared. So rho squared cancel, and we end up with rho in the denominator, and additional factor is in here. At z equals 0, when z reaches at this point, z equals 0, it becomes a very simple formula. At z equals 0, the magnetic field is in this direction. Even after that, magnetic field is still in the direction, because it's along the symmetry axis. But if you deviate, the magnetic field should be something like this direction. B field will be like that. In the next problem, we will consider the case where the field point is not on the z-axis symmetry axis, but it's deviate from a little bit. Force between two parallel currents. We have current I, A, and IB, two currents. For example, IA generates the magnetic field, and here magnetic field is along this direction due to A is along this direction. And charge Q is flowing upward. QV is in this direction. So we have magnetic force QV equals to B, or IL equals to B. This is the length L. Magnetic force is toward the other current when they are parallel, and if the current is opposite, then the direction will be flipped. Therefore, the parallel currents IA, IB parallel, they have attractive force, and anti-parallel current, they are repulsive. And detailed computation is given in here. A nice example is a railgun, and please follow the detailed derivation for the railgun, how it projects, how to shoot a projectile in a very fast way. Next, we consider Ampere's law. Ampere's law is equivalent to Biot-Savart law. Biot-Savart law is like the Coulomb's law. For E field, Biot-Savart law is for the B field. The direct calculation is B field and direct calculation of E field. Gauss law uses a symmetry to find out the electric field in an easy way. Ampere's law uses a symmetry to compute the magnetic field. So Ampere law is more convenient than Biot-Savart law. Gauss law is more convenient than Coulomb's law. However, if there is no such a symmetry, then we have to stick to Biot-Savart law or Coulomb's law. This is Ampere's law. There is a closed curve. Closed curve surrounds a surface. So C is boundary of some surface. This is surface. Passing through the surface, some current density is flowing out that we can integrate over the surface of the current density. We'll find the current. And this current is called enclosed current. Enclosed current means this curve C encloses the surface, and the current I is the sum of current densities, a kind of flux integrated over the surface enclosed by the closed curve C. In that case, the answer is you integrate over the curve of magnetic field scalar product with the displacement over the curve, and this curve is closed, so you put a circle on the integral notation, integral symbol. Thus, it is called Ampere's law. Amperian, when we use Gauss law, we use some volume. We enclose some volume with the surface. The surface is a boundary of some volume, and we call this surface as a Gaussian surface. And we were interested in the charge enclosed by the surface. When we use Ampere's law, there are currents sometimes coming out, coming into the loop C encloses various currents. It's called Amperian loop. And this curve is the boundary of the surface. Boundary of the surface. And the current I is summed over the surface as a current density. And in a discrete case, In a discrete case, it is just the sum of currents enclosed. Okay. The direction of the surface is counterclockwise, so that this direction is a positive, this direction is negative. Using Ampere law, for example, we have a straight current, a current I along a straight line, infinite straight wire. Then the magnetic field will be generated by symmetry. It's along a circle. We use a radius rho, applying Ampere's law. Magnetic field B and this curved element, they are parallel. So B dot ds vector should be B dot 2 pi rho, and that is mu 0 multiplied by the current. This is current enclosed by this Amperian loop. Then the magnetic field B magnitude is mu 0 I over 2 pi. And we know by symmetry the magnetic field must be along the tangential direction, and that is what we have obtained previously by making use of the Usability Law. The magnetic field generated by a current along a straight line. Next, we consider the magnetic field inside the long straight wire with current. In this case, current is distributed as a current density over a certain area. For simplicity, our current density is assumed to be constant, so that J dot dA equals J times A, and it is a circle, is a 2 pi radius R, not 2 pi. Pi R squared, and the net amount is I. So uniform current density and the total current itself is I, and I is distributed evenly over a surface. And we assume that radius of this wire is capital R. We introduce an Amperian loop of radius rho, and rho ranges from 0 to R. In this region, the current density changes depending on the surface, and if rho is greater than R, J dot dA, this one is I and is fixed. We use these coordinates, cylindrical coordinates, and use the Ampere loop and compute the magnetic field. Assume that magnetic field is circular. Yes. Therefore, along the Ampere loop, B dot ds is just magnitude depending on the radius rho multiplied by 2 pi rho, and is mu0 times current enclosed by the surface. Current I is flowing in area of pi r squared, and what happens if I shrink the size with rho with the uniform current density, then the I enclosed by radius rho is just I times rho over r squared, because the area is pi r squared. This area is a pi rho squared. And when rho is greater than r, the current, this one or this one, any curve encloses current I. They are fixed. The integral is just left-hand side integral is the 2 pi rho b rho. Finally, substituting the I enclosed in here and substitute this one in the left, our final result is this and this, depending on the radius, and it is always tangential. In summary, Ampere's law can be used to compute complicated but having symmetry, complicated current density distribution. But if there is a symmetry, the magnetic field can be computed very easily. These are the examples, so you can study by yourself. Solenoids and toroids. Solenoids, straight wire, it generates magnetic field in this way. If we have many wires parallel, magnetic field is generated in this way, because another wire in between, they cancel. Outside they are parallel, inside they are parallel. So if there is some current flowing this way, magnetic field is something like that. In addition, if I have a surface, the current is flowing in this direction, then magnetic field is like that. However, inside this area is very small, and outside is an infinite area. So resultant magnetic field is concentrated inside, and outside the magnitude is much weaker, and in ideal case it is concentrating inside and outside vanishing. We can make use of Gauss Ampere's law to find the magnetic field inside the solenoid, that is like this. As shown in this figure, magnetic field inside the solenoid is very strong inside, but outside is weak. We can choose an Ampere loop in such a way. So magnetic field inside strong. So in B dot ds, the mu 0 I enclosed, this contribution, all are vanishing. Only this contribution, B times H, survives. And what is I enclosed? Why I enclosed? N turns per length H. Then because wire has current I, so it's coming out, going into. N turns per length H. So this is I. So there are n i's. N times I is the I enclosed. Therefore, magnetic field mu 0 n I, and magnetic field is mu 0 n I, where n is capital N H, and this is H and number of turns in H. So number of turns per length. So magnetic field inside the solenoid is like that. We can extend this result to consider the magnetic field inside the toroid. Toroid is just like a donut. We can prepare Ampere loop inside, just like the solenoid, only B is inside, B outside can be approximated as B equals 0 outside. Again, we can make use of Ampere loop of radius r between these two. Here, no current passing. Here, we have many currents passing. I enclosed. Here, current is flowing in this way. So inside is into the page, out of the page. Anyway, into the page. So if I have a radius r of Ampere loop, we have these currents. These currents are number of turns multiplied by single current. Again, Amperian loop with radius rho has a magnetic field rho whose direction is tangential direction to. Therefore, again, this left-hand side integral is a magnetic field magnitude multiplied by the circumference. Finally, I enclosed is the single current multiplied by the number of turns. And this factor is divided here. Next, we consider rather difficult problem, but interesting problem. There is a current on the xy plane on a circle of radius A, and we have a field point. Previously, we selected the field point on the symmetry axis, but we have additional deviation of rho that is perpendicular distance from the symmetry axis. So the current is flowing on a wire of radius A. We assume that radius A is a very small, and we have the magnetic dipole moment is I times pi A squared. This is area and current directed along the z-axis. We have x prime and y prime to represent the wire element of ds. So we have a circular current. This one has ds, and this coordinate is x prime, y prime. And x prime, y prime is a cosine phi prime, a sine phi prime. And we have field point P. Field point P, this is x, y, z. For simplicity, the rho equals x squared plus y squared. For simplicity, we choose the rho, 0, z. And then we integrate over the circle to find out the magnetic field. Here, if I want to apply the Usability Law, we have to know that vector, this is a capital R, from the source to the field point. Source is this one. This one is placed at rho hat vector. For simplicity, we have chosen it is a rho I hat only. And field point is this is field point. Plus zk hat. So plus zk hat. This is the field point. So field point subtracted by ds is placed at rho hat, a rho hat, that is a cosine phi I hat plus a sine phi prime j hat. So subtract the field point by the source point. We have this, and x prime, y prime, x prime equals a cosine phi prime, y prime equals a sine phi prime. So this is the capital R that connects the wire element and the field point. The magnitude of R squared will be multiplied in the denominator to find in magnitude of R squared here. The unit vector is divided by the magnitude. So R divided by magnitude will be the unit vector. So we compute ds cross R hat. That is, R hat is R vector divided by magnitude of R. And we make use of the determinant to find out the ds cross R. Substituting this one into Usability Law, we have this expression. We shall find that this sign-dependent integral vanishes. Any cosine-dependent integral or the constant integral survives. These are the explanation. The cosine phi is an even function. We integrate over 0 to 2 pi to phi prime, or this one is the same as minus pi to phi prime. And we have the result, very complicated. This is complete elliptic integral. This is out of the scope of our class. However, we can expand the denominator in powers of a, because a is assumed to be very small. And then the expansion can be made by making use of the binomial expansion. And the result for the integrals are given in here, where r here. Capital R is connecting the source and field point, and small r vector connects the center to the field point. And we can express this one, this cosine integral and 1 integral can be expanded in powers of a, and we keep the linear term for a only. If you make use of integral table and substitute this result into this expression, what we have finally is of the form. Now, magnetic dipole moment, the magnitude of the dipole moment is current times area. So magnetic dipole moment, magnitude, and the circle, this circular current has a normal vector along the k direction. So this one is the magnetic dipole moment. If we replace this magnetic dipole moment and make use of these simple identities, we end up with the expression for the magnetic field as a goes to 0, but keeping this non-zero, neglecting any higher order terms in a, small a. This is a radius of this circular wire. We end up with the magnetic field. That is, usually we have a magnetic dipole. We drew the magnetic field line like that. This one is actually coming from this expression. This is the magnetic field, and this is the magnetic dipole. Magnetic dipole generates the magnetic field in such a way. The remaining part is a simple application of derivation. And finally, we reconsider the Ampere's law. And Ampere's law, on the right side, there is a current. And that current is expressed as a surface integral of a current density. Substitute this one and move to the left-hand side and shrink the size of surface into a very small surface. Then it reaches a point. That means that this integral vanishes for any such surface. It's a tiny surface. That means just a point, and the integral must vanish. That means we can obtain the Ampere's law of this integral form, this is Ampere's law for the differential form. So until now, we have Maxwell's equation for the electric field, magnetic field does not have a monopole, and we have Ampere's law, curl B equals U0J. This is Ampere's law. Actually, the Faraday's law will lead to the curl of electric field. And actually, these four, we will soon complete the four equations. These are the Maxwell's equation